before we start, okay. Before we start, I'd like to know if there are any questions about what we have seen so far. No questions? Okay. Then let's begin then. Okay, so today we're going to talk mostly about spectroscopy, molecular spectroscopy. So I have to remind you a little bit of how this works from the physical viewpoint. But before we do that, I have to go a little bit deeper into the product representation that we discussed very briefly at the end of last lecture. Okay, so, well, I mean, the aim today, if I have time at the end of today's lecture, you will be able to obtain this part of the predictions from group theory. You will be able to state the microwave, infrared, and Raman activity of molecules for methane or for deuterated methane. Okay, so now let's remember the product representation. Okay, so the idea is that ordinary vectors that live in R3 transforms like the coordinates. Okay, and they belong to the vector representation. On the other hand, rank 2 tensors, like the polarizability of a molecule, live on the tensor product of R3 times R3 and transform like products of coordinates. Okay, so it means that this transforms like xi or ei, ej. So I need two matrices from the vector representation. And this, by definition, is the product representation. Okay, you realize that this is in principle a 9 by 9 representation because general tensors have 9 independent components. In the case of polarizability, that's a particular case because they are symmetric. They only have 6 independent components, but we are speaking in general. Okay. Now I'm going to prove something that I gave you without proof last time, how you compute the character of a product representation. And this is really simple. It's a matter of being careful about indices. So that's the way vectors like the electric field transform. So this is the matrix for the vector representation. And by definition, I obtain the character by computing all the traces. How do I compute a trace? Just by taking I equal to j and summing over I, the repeat index convention. So that's very simple. If I have the matrix, all I have to do is I have to equate the two indices and sum over them. Now, what happens with the product representation? The product representation here, I mean, for the vector, I have a vector which has a simple index. Now, tensors are also vectors. Why? Because tensors live in the tensor product space. I just take the tensor product between different spaces. But the tensor product of linear spaces, as you know from general algebra, is also a linear space. So these things are linear objects. They are vectors, but that have two indices, I and j. So the analogous of this is this. But if I want to make the analogy closer, what I do is I define this v squared. Okay, I simply say v squared with indices ij and kl. This would be the matrix in the product representation. Okay, why? Because this takes on n values, because I have 9 possibilities for the double indices. This takes on 9 values. And I define, this is just a definition, this product, I rewrite it like this. What is the advantage? The advantage of doing this is that now this equation is formally identical to this one. The only difference is that here I have single indices, here I have double indices. So instead of J, I have KL. Instead of I have IJ. Here I have I, IJ, IJ, J, J, KL, KL. So it's just there's just a trick. There is nothing fundamental. This product of matrices, I define as a matrix, which is larger, it's a 9 by 9 matrix, in the product representation by this identity. Is that clear? So there is something important. You remember that when we saw the addition of representations, I told you, be careful because adding representations has nothing to do with adding matrices. If I have a representation which is the sum of 2 representations, this doesn't mean that the matrices of the sum are just the sum of the matrices. And with the product, it's exactly the same thing. V squared is the product representation of V times V. But the matrices of V squared are not the product of these matrices. I mean, the product is something very different. With V, I will have to write IJ, JL, and it will give me just a matrix IL. No. From 2 matrices, which are 3 by 3, I obtain a matrix which is 9 by 9. This is known as the Chronicle product of matrices. I don't know if you have seen it before or not. This is used very much. For instance, when you want to represent 4 by 4 matrices in terms of polymatrices, things like that. This is done all the time. If you use Mathematica, Mathematica has a function which is called Chronicle product that automatically takes you the Chronicle product of matrices. And this is actually the product involved in the product representation. In fact, sometimes people, the product representations, instead of writing V cross V, write V O times V. I mean, the sign for the tensor product, okay? But now, once I have defined this, it's very easy to find the trace. Here, these 2 indices have to be equal. Here, these double indices have to be equal. So if I write here IJ, here I have to write IJ, and that's the whole thing. So that's the definition. And now I take the trace by making these 2 indices equal, IJ equal KL. So the trace, the character for G is just the trace of V square of G, and it's just this with IJ equal to IJ. But now identifying this I is here, this J there, this happens to be this. But this, you see, this is a trace by itself, and this is a trace by itself. So this is the trace of V squared. So this is the rule that I gave you, that when you have a product representation, all you have to do is to take the products of characters. Simply, it's very simple, but there is some index gymnastics here. If you are not used to it, just go through it, but it's really simple. I have done the thing in detail for the product representation of vector times vector. You can do this for any 2 representations. We'll do that in a minute. But let's see an example. For the group C3V, this is the character table with the irreps of the vector representation. So now we want to construct the character table for V square, the product representation. But I know that all I have to do is to take the square of the matrices, of the traces. So this is trivial. And now, of course, whenever I have a new representation, I can decompose it. And we are going to need this today. In fact, to decompose it, all I have to do is to use the magic formula. By now you are experts in doing this kind of computation. So this tells you that V squared decomposes this way. This will be essential to find the Raman activity. This computation of V squared, well, in fact, of the symmetry is V squared. That's something closely related. Okay, so now this is completely general. If I have 2 different representations, D1 and D2, with dimensions D1 and D2, the tensors in this tensor product belong to the product representation. So now these are tensors where the first index lives in this space, the other index lives in another space, but the formula, you can check that it goes through exactly. I mean, yes, it's just the product of characters. Okay. So now we are going to see the microwave and infrared activity. And before I do that, I want to remind you, and maybe some of you don't even know the stuff that I'm going to say, to talk about. So I'm going to speak a little about the spectroscopy of molecules. So let's stop sharing this. We need the camera. And now I'm going to do this on the blackboard. So first, I'm going to talk about microwave and infrared spectroscopy of molecules. Okay, now the first thing you have to know is that the microwave is related to the rotational spectrum. The rotational spectrum of a molecule. And infrared is related with the vibration spectrum. And both of these techniques are mostly absorption. Basically, I have a gas with molecules. I mean, probably this can also be done with liquids, but I don't really know the experimental details. You have a gas with molecules, some CH4, and I shine here some infrared light, and I observe some absorption. Okay, part of this infrared light is absorbed. So that gives me information about the vibrational spectrum, which are the eigenfrequencies of the molecule, which are the vibration frequencies. I can do the same thing with microwaves, and this is very important, for instance, for astrophysics, because sometimes you can study how microwaves transmit across very huge molecular clouds and things like that. And this gives me information about the rotation spectrum of the molecules. Okay, so how does it happen? Well, you know, I mean, probably all of you have studied the interaction between atoms and electromagnetic radiation, and you know that the lowest order approximation is the so-called dipole, the electric dipole approximation. And what's the idea? The idea is that you have a system, can be a molecule, can be an atom. The system is always a collection of charges. And you know that whenever you have a collection of charges, you can describe this by giving the total charge. You can give the dipole moment with respect to the center of charge. You can give the quadrupole moment, which is a tensor, the octupole moment, etc. You have a multiple expansion. And if you want to study the interaction of radiation with a system of charges, the lower, I mean, the biggest effects, if they are different from zero, are always in the electric dipole approximation. So basically, this means that from all this distribution of charge, the only thing that matters to us is the dipole moment, P, which, as you know, is just this. The sum, these are the charges, these are the position with respect to the center of charge. Okay. We assume that all these things are neutral, so there is no charge. So to lead in order, that's the thing that really matters. So that's one thing. And today we will care only about dipoles, not quadrupoles, not any other thing. Now, the next thing that you have to remember, or to know, how are these spectrums? Well, rotational spectrum, the rotational spectrum can be very complicated. In fact, you've probably never studied what is the rotational spectrum of something which has three different principal moments of inertia. It cannot be done analytically. And most books don't even consider this case. But if you go to Landau analysis, the volume on non-relativistic quantum mechanics, you will find it very well displayed. We are going to consider the simplest case. The simplest case is a diatomic molecule. And for a diatomic molecule, the L always perpendicular to the axis. And the energy, Hamiltonian, is just given by this. I is the moment of inertia. So the eigenvalues are trivial to find. So you have a spectrum with different levels. I mean, they are not equally spaced. Okay. So since they are not equally spaced, means that when there are transitions, you have many different frequencies. Okay. In fact, in the spectrum of absorption, you find a lot of equally spaced frequencies corresponding to different levels. Okay, you can see that all this, I mean, ER -1 is some constant that usually people call to be L. So you have a lot of equally spaced absorption lines or emission lines if you are studying the spectrum of emission. Here, the selection rule to obtain this is delta L at the electric dipole approximation +/-1. Okay, so you just have to consider consecutive levels. So this is the rotational spectrum of the molecule. Now, how I absorb it using a spectroscopy? Well, in the dipole approximation, I need a molecule that has a permanent dipole, P0. For instance, like hydrogen chloride. Okay, if I have something like hydrogen, this doesn't have any permanent on any equilibrium dipole moment. So this cannot be observed in microwave, okay? Because it doesn't have a dipole. However, the hydrogen chloride has a, obviously, because this is going to be negative, this is going to be positive. It's a very ionic molecule, and I will have a permanent momentum. Classically, the picture is very simple. I have some P0. If the molecule is rotating, this P0 is rotating. So if this is rotating, it has two components. Let's see, Px equal P0 cosine omega t, and Py so it means that I have oscillating dipoles. Whenever I have oscillating dipoles, I have radiation. This is going to emit, or this is going to absorb. And this is going to emit or absorb classically with the rotation frequency of the molecule. At the quantum level, you have to do the previous analysis and you find a discrete set of frequencies. I mean, frequencies are equally spaced. So you can observe many different frequencies. Now, so here, from the physical point of view, a molecule is microwave active if it has a permanent dipole moment. If it doesn't, it's not active. Okay. So this means that in principle, in the case of this simple molecular, is very simple. But if I have a complicated molecular with many atoms, well, you have to start to compute the dipole moment. You have to know the charge distribution. That's a mess. We'll see that using group theory, the thing is automatic. It takes 5 seconds to know whether a molecule is microwave active or not. All you have to know is the vector representation for that molecule. We'll see that in a minute. Okay. So much about microwave spectrum. Why is this called microwave? Well, because the rotation levels are closely spaced, so these frequencies are rather low. Okay, so they fall into the microwave spectrum, centimeters, millimeters. So these are really radio waves. So that's the reason they are important astrophysically. Now, infrared. What is the infrared spectrum? Well, you can have, for instance, the hydrogen molecule. And obviously, this can vibrate like this. Okay. You can also have the hydrogen chloride molecule, and it can also vibrate. So basically, in order to have infrared activity, you need delta P, not a P0. P0 doesn't matter. You need something that oscillates due to the vibration of the molecule. Now, in the case of hydrogen, you see that when I separate the atoms, I don't create any oscillating dipole because this is plus, there is no dipole moment here. So this is inactive. In the case of hydrogen chloride, this is negative, this is positive. It has a permanent dipole moment, but also this dipole moment changes if this thing oscillates. So this creates a delta P, which is a function of T. So basically, from the physical viewpoint, a molecule is going to be infrared active if a mode is going to be infrared active if this mode induces a time-dependent momentum, a dipole moment. Well, in this case, this is trivial. Let me show you a slightly, less trivial case. You can consider, for instance, the boron, the fluoride molecule, which is a planar molecule, and you have studied it, you know everything about the spectrum. Well, one normal mode of vibration is this. This is usually called a breathing mode. These modes also appear in crystals. So it's obvious that if the molecule is vibrating like this with this address, this is of course positive, this is negative, negative, yes. I don't induce any dipole moment, much less an oscillating dipole moment. So of course this doesn't radiate, this doesn't absorb anything. So this mode, this particular mode is infrared, non-active. However, I can consider different modes. Another mode for this molecule is something like this. If you diagonalize the dynamical matrix, you can obtain, no, sorry, this is reverse, mode like this, roughly. These three atoms move up. This can go also a bit sideways also, and this moves down. So in this case, since this is negative and this is positive, I induce some delta P, which is oscillating. So this mode is active. Well, you realize that when you have a slightly more complicated molecule, it's a terrible mess to analyze this. You have to have a very good spatial vision. You have to have the normal modes. Well, if you know group theory, it's an extremely simple computation to see which modes are active and which are not. Okay, so that's what I'm going to explain now. Before I do, are there any questions regarding the microwave and infrared activity of molecules? No questions? Okay, so then we'll move to the group theory part. Okay, well, I leave this thing for the end. Well, sorry, I should have explained that before I move into the spectroscopy, but that's very simple. And in fact, that's something that was already in the last slide of last lecture. Okay, so now that we know about the product representation, it's very easy to know when you have bilinear invariance. If you want to construct Hamiltonians, if you want to construct dynamical matrices, potential matrices, anything, all these things have to respect the symmetries of the system. So the trick to construct these objects is just to take products of representations. If you take one representation tau1 with this basis, x1, sd1, and another representation irreducible and real, representation τ2 with these coordinates, okay? And then I look for bilinears, and I want to find bilinear invariance, like we did last time when we compute, for instance, the dynamical metrics, I mean the potential energy metrics, and we compute the polarizability tensor. Okay, so basically the bilinears, by definition, transform or belong to the product representation. Okay, this product representation, I use tau here, but in general need not be reducible. I mean, this is really a typo. I should have written T3 because I'm assuming that these are irreps, but you know that when you multiply two irreps in general, the thing is reducible. Okay, so this is a typo. I'll correct this. Now, the number of bilinear invariants is equal to the number of times the identity representation is contained in tau 3. Why is that? Well, bilinears transform according to this. When I decompose this will be A1 plus A2, and each of these things will have some coordinates, which will be a bilinear. Now, if the A1 representation appears here, the identity representation means that the corresponding bilinear transforms like the identity representation. And remember, the identity representation was 1, 1, 1, 1, 1. Nothing changes, so that's an invariant. So basically, I have as many invariants as the multiplicity of the identity representation. Okay, we'll see that in a minute, we'll see in practice, and that's a lot easier to understand. So basically, I use the magic formula to see how many times the unit representation for the identity representation of characters are 1, as you remember, are contained in T3. I have to take the complex conjugate, but since I'm assuming that they are real, we'll consider the complex case in the next few lectures. This is just this product. I mean, this character is the product of these characters, or these two characters, okay? But now, this is equal to the complex conjugate, so this is just the scalar product between these two characters. And you know that the scalar product of two characters of irreducible representations is equal to 1 if they are equivalent and to 0 otherwise. So what does it mean? Well, this simply means that if tau 1 is not equivalent to tau 2, this is 0. So the identity representation doesn't appear in the decomposition, so it means that there are no bilinear invariants. So the only way to get bilinear invariants when you multiply irreps is by multiplying an irrep by itself, okay? By the same representation or equivalent, which is the same, okay? And for equivalent representations, the only bilinear, we knew what it was just the scalar product, okay? So remember, last time we used the fact that the scalar product was an invariant. Now we have proof that that's the only invariant that I can construct. So now we are on firm ground. We know exactly how to construct all the bilinear invariants, okay? Something which is very important is the following thing. If the representations, the irreducible representations, are equivalent but are not identical because they are written in different bases, there is still an invariant, but it doesn't take such a simple form, okay? And next time I'll give you an exercise where you prove, this statement. So you have to be very careful. That's a very common mistake also. You have two irreps, they are equivalent, but they are written in different bases. Then the invariant that you construct is not this. This is not an invariant. It's something similar, it's bilinear, but it's much more complicated. So you have always to make sure that you use the same matrices for equivalent representations. If necessary, you have to make a change of basis. Okay. Any questions so far? Okay, so now let's move to spectroscopic activity of molecules. First, microwave activity. Remember that in order to have this activity on physical grounds, we need a permanent dipole. Now, when this dipole is at rest, when the molecule is at rest, it doesn't radiate because permanent dipole, there is no accelerations, non-accelerated charges cannot radiate or absorb radiation. Okay, but now if the molecule is rotating, this is going to be rotating, and then this has an electromagnetic activity. So the criteria is very simple. The molecule should have a permanent dipole moment. How do I formulate this from the group theory viewpoint? Well, it's very simple. A permanent dipole is a property of the molecule in equilibrium, and therefore this dipole must be invariant under the group of symmetry of the molecule. Why? Because if it is not invariant, that's not the symmetry group of the molecule. Okay. So now, on the other hand, P is a vector, so it belongs to the vector representation. So it means that some component of vectors have to be invariant. So this means that in the vector space, there must be a subspace that transforms according to the identity representation. Okay, so that's the criteria. You have a molecule, an extremely complicated molecule with 1,000 atoms, but you know the symmetry group. If you know the symmetry group from X-ray or from wherever, you immediately can compute the vector representation. And now you decompose the vector representations. If A1 is contained in the decomposition, the molecule is microwave active. Otherwise, it's not. So it's as simple as that. Now, methane, the vector representation for methane is irreducible, is T2, which is a three-dimensional representation. Therefore, the identity representation is not part of V. Therefore, this means that there doesn't exist any vector which is invariant under this group. Since this is the group of the molecule, this means that the molecule, there is no way it can have a permanent moment, dipole moment, because it wouldn't be invariant. And this is a contradiction. Okay, so just by knowing that V is equal to T2, you know that methane is not microwave active. You don't have to know anything else about the molecule, just the symmetry group. For deuterated methane, on the other hand, V, remember, had this decomposition. This means that vectors in the Z direction are invariant under all the transformations. So in this case, A1 is contained in V, therefore this is microwave active. And the dipole moment must be parallel to the C3 axis. So you see what a simple analysis, if you know group theory. Any questions? Okay, now infrared activity. As I mentioned, infrared activity is related to an oscillating dipole moment. The idea is that U is a deformation of the molecule that describes the oscillation of the molecule around the equilibrium positions. And now, if this thing is induced by the oscillations, then it's going to be active. Is this possible? Well, let's see. U belongs to the mechanical representation. It's a displacement of the molecule, and you know that the normal modes that diagonalize the potential energy matrix are a basis. Why are they a basis? For a very simple reason. You know that any Hermitian operator, when you diagonalize, you obtain a basis for the space. Now, the potential energy is Hermitian. Actually, it's not only Hermitian, it's symmetric because it's real. So the normal modes are a basis, okay, in the space of vibration. So it means that U can be written as a linear combination of normal modes. And you remember from your mechanics that the coordinates are what people call the normal coordinates. So any general displacement of the molecule is a linear combination of normal modes with time-dependent coefficients, and these time-dependent coefficients are the normal coordinates. These are the normal modes. Is this clear? So U is linear in the normal coordinates, okay? On the other hand, you know that the normal coordinates belong to the vibrational representation, okay? Because that's the definition of vibrational representation. It tells you how proper vibration of the molecule transforms. So now we use the same trick that we used last time. It's easier to work with something which is a scalar, like the Hamiltonian or like the energy. So if you have a dipole moment, oscillating dipole moment, the energy is given by the scalar product with the electric field. And on the other hand, we know that this delta P is a linear combination necessarily of the normal coordinates. So this belongs, this transforms according to the vector representation, this transforms according to the vibrational representation. So the infrared Hamiltonian that describes the interaction between electric field and dipole moments belongs to the product of V corresponding to E and VIV. So basically, if I want to construct this Hamiltonian, all I have to do is I have to find invariance in this product, bilinear invariance. And now we know how to do it. Okay. Basically, I have to decompose this thing into irreps, and I have to decompose this thing into irreps. Now you remember that each normal coordinate, each normal mode was associated to one of the irreps appearing in this decomposition. That's what we saw last time. So basically, assume that you have a vibration, a normal mode. This normal mode belongs to one representation. If this representation is contained also in V, you can construct a bilinear invariant. If the irrep according to which a normal mode transforms is not contained in V, there is no way I can construct a bilinear invariant, because remember, what we just proved is that the only way to get bilinear invariance is by multiplying an irrep by itself. So this is the criterion. A vibration mode belonging to the irreducible representation tau will be active in the infrared only if tau is contained in V, so that a bilinear invariant can be constructed. Okay, let's see an example. Let's do it for methane. For methane, that was the decomposition of the vibrational representation. That's what we did last time. These are the normal coordinates. Okay, this is V, the vector representation, which is irreducible for the group TD, is just T2 times EX, EY, EZ. So now I have to see how many invariants can I construct. Why? Because the Hamiltonian, we have just seen that has to be a linear combination of bilinear invariants. So if I construct this bilinear invariance, I know the form of the Hamiltonian with some independent coefficients, of course. Well, let's do this. You see, A1, there is A1 in V, but there is not A1 in V. So this cannot take part of the Hamiltonian. I cannot obtain any invariant by combining this with this. The same is true of this. However, this with this, I can construct an invariant, which is just the scalar product with some undetermined coefficient. And then this with this, I can construct this invariant, which is just the scalar product with two undetermined coefficients. Remember that group theory only tells you when a coefficient must be zero. That's the only information that you can get from group theory. So it tells you that any other bilinear, the coefficients have to be zero because they're not invariants, okay? But it never tells you the value of these coefficients. To compute the coefficients, you need physical input, okay? But at least it tells you that the infrared Hamiltonian, the most general form for the infrared Hamiltonian, I mean, the one that describes the interaction between electric field and normal modes of the molecule is this, in the electric dipole approximation. Of course, if you go to quadrupole, you'll have other things, but these are, as far as I know, these are extremely weak absorption lines, but it could be done by the same methods. I mean, there is no limitation to what you can do with group theory. So from this, we conclude that the two triply degenerate frequencies, which are this and this, remember that is three frequencies, these three modes have the same frequency because they belong to the irreducible representation. They are both of them, they are active. You see that to give this answer, I don't even need to construct this. I mean, this is useful for other things, as you'll see in the problem set. But all I have to see is this is T2. T2 is contained in V, okay, active. T2 is contained in V, okay, active. This is inactive. So it's extremely simple, okay? Any questions so far?
But you don't only need to know that it's contained, but you also need to know that it's contained twice with different coordinates, right?
Yes, that is contained twice. Okay, if you want to construct the Hamiltonian, you need to know that it's contained twice, and also because if this is contained twice, it means that there are two different frequencies, okay? All these three modes have one frequency, which is whatever, and all these three modes have another frequency. So the multiplicity tells you that there are two infrared active frequencies associated to T2. So it's true. If you want to know how many infrared frequencies you have, you really need to know that the multiplicity is 2. So basically, all you need is something that you already know how to do, which is the decomposition of the vibrational representation. I mean, remember, there is 1, 2, 3, and 4 different frequencies. Out of these 4 frequencies, these 2 are active. Okay, is that clear? Or... Okay.
Yes.
Yeah. Any other questions? Okay, let's do the same thing for the deuterated methane. For deuterated methane, both decompositions are different. They are very different. This is reducible. This is A1 and E, and this is like this. So now you see, I'm not going to construct the Hamiltonian. You can do this. I think you are supposed to do this in one exercise. But you see that A1 is contained in V. So from here, you could construct 3 invariants corresponding to these 3 frequencies. So these 3 frequencies are infrared active, and also these 3 frequencies are also infrared active because the corresponding irrep is contained in V, and you can construct an interaction Hamiltonian. So this means that these modes interact with the electric field. Okay. Okay, before we move on to the Raman Raman activity, let me point out something. Nobody has asked me one question. If you remember, last time I used lowercase q in this decomposition. Now I'm using capital Q. Why is that? Why have I changed from lowercase to capital Q? Do you have any idea why I did that? Well, when I write lowercase, what I mean is symmetry adapted coordinates. Okay, so lowercase, that's what I used last time, are supposed to be symmetry adapted coordinates. Each of these things is the coordinate corresponding to a mode of a set of displacements of the molecule that transform according to one irreducible representation. So these are just symmetry adapted coordinates. Okay. Now here, when I use capital Q, what I mean is normal coordinates. They are not exactly the same. When I use symmetry adapted coordinates, I get the block diagonal structure for the potential matrix. Okay. Remember, the potential matrix has a block diagonal form, which is given by Wigner theorem. But to exhibit that form, I need to use special coordinates, which are called symmetry adapted coordinates. In the same way that for the vector representation, I have to use x, y, and z if I want to have the block structure. Okay. However, these are stronger than symmetry adapted coordinates. Normal coordinates, in normal coordinates, the potential matrix is diagonal, not block diagonal, but diagonal. Why? Because the normal coordinates are the coefficients. What is that? Are the coefficients of the normal modes, and the normal modes have each of them has a definite frequency. They diagonalize the matrix. Okay, so that's the difference. So the idea is that, of course, normal coordinates are automatically symmetry adapted coordinates in the sense that I get a block diagonal structure, but I get a very specific block diagonal structure, which is a completely diagonal structure. Okay, so now, since A1, remember that A1 automatically Q1 was a normal coordinate and the corresponding mode was a normal mode because I didn't have to diagonalize anything. This was already diagonal because the multiplicity is 1. The same was true for E. I didn't have to diagonalize anything. So I can say that capital Q1 is equal to lowercase q1. And the same is true for this. However, since this T2, the multiplicity is 2, I had to diagonalize a 2 by 2 matrix, which appear 3 times, exactly the same matrix. So these normal modes are linear combinations of the corresponding symmetry adapted coordinates. In fact, Q4, capital case Q4 is a linear combination of lowercase q4 and q7. Capital case Q5 is a linear combination of lowercase q5 and q8, etc. Okay, so that's the reason that here I'm using, because here I'm speaking about frequencies. I mean, symmetry adapted modes in general, they are not eigenmodes of a system. They don't have any particular frequency associated to them. These do have, okay? Okay, so now, before moving on to the Raman activity, I have Raman activity, as we'll see, is related with the polarizability tensor. Now, the polarizability tensor of a matrix, of a molecule, is not just a second rank tensor, a rank 2 tensor, it's a symmetric rank 2 tensor, okay? So I have to make a distinction between tensors, general tensors, and symmetric tensors. And that's what I'm going to do now. So rank 2 tensors live in a 9-dimensional space, R3 tensor product with R3. This is O times that I mentioned before. And transform like these products, okay? The 9 possible products. That's the definition of tensor. That's something that transforms like the product of the coordinates. Now, rank 2 symmetric tensors live in a 6-dimensional subspace of R3 and transform like the symmetric products of just single coordinates. I mean, here I have R1 and 2. Here I only have just one set of coordinates. Why? Because if the tensor is symmetric, there is no distinction between x1, y2, and y1, x2. I mean, T12 is the same as T21. So how do I get this? Just by taking just a product of xyz with xyz. So the idea is that symmetric tensors transform like the symmetric products of coordinates, which are just this. I mean, obviously xy is the same as yx. However, x1, a2 is not the same as y1, x2. These two things are different and correspond to non-symmetric tensors. Xy equal to yx correspond to symmetric tensors. So symmetric tensors live in a 6-dimensional subspace. Now, one can show, in some books you can find this, I think this is probably done in Bradley. This is certainly done with all generality in the book by Lubarsky. You can obtain, I mean, this is the formula that gives you, this is called, I mean, the symmetric rank 2 symmetric tensors belong to the symmetrized square of the vector representation of the second symmetric power of V. And the characters are given by this formula. It's a bit more complicated. This is like for the vector, this part here, but then I have to compute also the square of elements, okay? I'm not going to prove this. It's not difficult, but you can do this up in books. I'll just give you an example of how this works. So this is the group C3b. These are the elements. I have to compute also the squares of the elements. The square of E, the identity is obviously the identity. The square of C3 plus is C3 minus, and of C3 minus is C3 plus, but they're in the same class, so that matters. And the square of a reflection plane is obviously the identity. If I reflect twice on a plane, I go back to the original, I come back to the original. So these are the elements, G, and the square of the elements. So I need now the character for the elements, which are given by this, and the characters for the square of the elements. So now you see these are the same because these are in the same class, but these are not. The element is a mirror that has character 1, but the square of a mirror is the identity, which has character 3. And now I just use this formula. I just take this square plus this and divide by 2. This gives me 9 plus 3, 12 divided by 2, 6. This gives me 0. This would be this square, which is 1, plus this, which is 4, divided by 2, 2. So it's extremely simple. That's all the computation that you have to do to be able to, we'll see in a minute, to find the Raman activity of molecules. What you have to do is to be able to construct the character for the symmetric product. Then you can use the magic formula, I'm not going to do it again, and you can decompose it, okay? So this can be generalized to different representations, T1, T2. It is like this, as you know. Of course, the symmetric product cannot be generalized to different things because it cannot be symmetric. It's only to one representation. I mean, to have a symmetric object, I always have to have equal spaces. So, but the formula is still the same, okay? So the next thing is Raman activity, but again, I'm going to give you some idea of what Raman spectroscopy is. Some of you already know, but I'm going to remind it to you. So let's stop sharing. Now, yes. Okay. I'm going to get some extra water, so just excuse me a minute. Let's take a little break. Okay, are there any questions before I explain something about Raman spectroscopy? Okay, Raman spectroscopy has to do with the Born-Oppenheimer approximation. When you have a molecule, you have the nuclei, the ions, and now these things can rotate, these things can vibrate, I told you, but then you have the electrons. The electrons, the valence electrons, are like a cloud surrounding all of this. And now you know that by the Born-Oppenheimer approximation, the idea is that electrons, I mean, the electronic mass is much smaller than the nuclear masses, and therefore they move much faster, and they really follow almost instantaneously the motions of the nuclei. So this means that this cloud, if the molecule rotates, the cloud rotates with the electron cloud rotates with the molecule, okay? If the molecule vibrates, the cloud is distorted. For instance, if the molecule vibrates like this, the cloud immediately adapts and is distorted, okay? So that's the first thing. I mean, to understand Raman, you first to remember the Born-Oppenheimer approximation. You have slow degrees of freedom, which are the ions or the nuclei, and then you have fast degrees of freedom, which are just the electrons, the electronic cloud, okay? Now, you remember that you have the molecule, and this is the electronic cloud. If you apply an electric field, this responds very fast to the electric field. So in general, you have the electric field induces an electronic dipole moment. I mean, this dipole moment is due to the deformation mostly of the electronic cloud. And this is the polarizability, the electronic polarizability, I mean, which gives you the response of this dipole moment to the electric field. So that's the second thing that you have to know. So this involves this tensor, which is, as you know, belongs to V square, because it's a symmetric rank 2 tensor. Okay. Now, what is the, so far, we haven't mentioned the electrons. I mean, the molecule has three different kinds of a spectrum. It has a rotation spectrum, which is in the microwave. It has a vibration spectrum, which is roughly infrared. So this is around 1 eV, this is much smaller. And then it has an electronic spectrum. You have many electron states. I mean, this has to do with chemistry a lot. And these are mostly in the visible, I mean, ultraviolet, visible, these are higher energies, okay? And we haven't said anything about this, and we are not going to say anything about this. Basically, because, well, Raman is not related to absorption or to emission of anything, like in the case of infrared or microwave. I mean, if you really want to probe a spectrum, in general, to probe it directly, you need to absorb photons, because the energy of the photons immediately tells you the difference in energies of the levels, okay? Or emit photons, because this tells you the same information. However, we are not going to speak of resonant absorption by the electronic cloud or of resonant emission. If you really want to know something about the electronic spectrum of the molecule, you need to have resonant absorption or emission. Instead of this, we are going to consider something which is called Rayleigh Scanning, which, as you know, is responsible, for instance, for our blue skies. Okay. Now, what is Rayleigh scattering? This is a very simple idea. You have your molecule and you have your cloud. If you apply an oscillating electric field, you immediately get a dipole. It's a tensor in general. They are not, these things are not parallel. So this induces dipole, maybe like this. EFT doesn't have to be parallel, and this is oscillating. So it means that if I send electromagnetic waves at a classical level, this thing radiates, scatters. Okay, so that creates the blue color in our sky. Okay, this doesn't mean that the photons are absorbed and then re-emitted. No, no, this is a non-resonant scattering. Okay, we are far from resonances of the electronic cloud. We are not considering that. Okay, so this is just scattering. It's not absorption or emission, it's just scattering. Okay, and this can be described pretty well almost at the classical level. So you probably know. Well, so now this is Rayleigh scattering. Rayleigh scattering is interesting, but it doesn't give you any information about microwave or infrared spectrum of the molecule. However, something very interesting may happen. This is electronic. Assume that this is the electronic cloud for some molecule. For instance, this could be hydrogen. So that this is the electronic cloud for hydrogen. It's going to have some more symmetry. And this is described by this polarizability tensor. The response of this cloud to the electric field is described by this polarizability tensor. And you know that rank 2 tensors can be represented, symmetric tensors, more or less like ellipsoids, okay, or paraboloids, I mean, general conic sections, quadratic or things like that. So now assume that the molecule is rotating. If the molecule is rotating, what's going to happen? The cloud is going to be rotating around. This thing is going to have time dependence. So now this, I mean, if this thing is not rotating, this is a constant, and this thing follows exactly the time dependence of the electric field. However, if this thing is rotating, you are going to have some kind of amplitude modulation, because you are going to multiply two things that depend on time. This is going to have a frequency omega 0, which is the frequency of the electric field, but this is going to be some frequency, which is the frequency of rotation. And when you multiply these two things, you are going to get the sum and the difference. So this means the following thing. This means that when you scatter light on a molecule which is rotating, you are going to observe the Rayleigh line, Rayleigh, which is just omega 0. But then you are going to observe also other frequencies. This is a classical analysis. You can do it also at the quantum level. Classically, it could rotate within a frequency. You have a continuum spectrum. At the quantum level, you know that there are some discrete rotation levels, so you find just some lines. So this is called rotational Raman. So you can get information about the rotation levels of the molecule just by doing Rayleigh scattering. And then what happens is that the scatter waves beside this wave, this component, which is huge, it's many, many orders of magnitudes bigger than the others. But then you have some small satellite frequencies, satellite lines, which just at frequencies which are the sum of the frequency of the incoming radiation plus or minus the rotation of the molecule. You can analyze this also at the quantum level. I'm not going to do it. But the important thing is just that this happens because I'm rotating this tensor. Okay? Now, is this going to happen for all the molecules? No. Consider, for instance, the methane molecule. Methane molecule is like this. It has a group TD, and you remember that we compute that this was like this. It was isotropic. The polarizability tensor was isotropic. Now, how do I rotate a tensor? I'm saying this thing rotates. Remember that the tensor I have to rotate just by a similarity transformation, something like this. This is the vector representation. This is the vector representation, and I just rotate it. Tensors rotate something like this. Okay. Now, if I do this, 3, 1, 3 minus 1, 3 minus 1. So if the tensor is isotropic, even if I rotate it, nothing happens. So you see immediately from this argument that CH4 is inactive in the in rotational Raman, just because this thing is isotropic. Okay. And why is this isotropic? This is isotropic because V is irreducible. If this is irreducible, the only invariant that I can form is E squared, Y squared, E squared. And this corresponds to this, to the identity. So this already gives you the criteria for Raman, for rotational Raman activity. If the vector representation is irreducible, there is no activity. However, in deuterated methane, and also for the other molecule that you have studied on your own, BF3, boron 3 fluoride, in that case, the tensor is like this. In the case of the deuterated, the decomposition is this. So I can form two invariants. This is squared, this norm, and this norm. So I have this, and then when I rotate this, this changes. This is not invariant, this is not the identity. I mean, this doesn't commute, this is not equal to carry. Because in general, this doesn't commute with all the matrices of the vector representation. Because not the identity. Okay, so you see what a simple thing when you view it from the group theory viewpoint. All you have to know is whether this is reducible or irreducible. The structure of the molecule doesn't matter at all. The only thing that matters is the group, the symmetry group of the molecule, and whether this is reducible or irreducible. Okay, so this is rotational Raman. You can also observe, and in fact, that's much more important, because in fact, the rotational spectrum, I mean, is useful in astrophysical context to identify the molecules. Okay, because if you can measure the rotation frequencies, you have some information about the moments of inertia, so that gives you some information, not very much information about the molecules. But the vibrational spectrum is much more important because then you really can identify completely a molecule from the vibrational spectrum. Now, what's the idea of the vibrational Raman? Well, it's very similar. You have your molecule. This is the cloud. If this thing vibrates, this goes like this, and this goes like this. The electrons follow instantaneously. This, and the cloud is the form. If the cloud is the form, this no longer has all the symmetries of the molecule, because this is the distorted molecule. So it means that this thing changes. There is a distortion. And this distortion doesn't have all the symmetries of the molecule. Next time, we will consider the concept of subduction. which is related with this. The fact that when you reduce the symmetry, new things arise. Okay. So, for instance, for the deuterated methane, this is the tensor. I think I wrote this wrong. Y and Z. This is alpha, but there is a delta alpha ij, and this delta alpha ij in general can have all kinds of elements. Okay, and these elements are changing in time. So when I write this, I have this. This has a frequency, which is the frequency of the incoming radiation. This has a frequency, which is the frequency of one of these modes. For instance, if this is a normal mode. And again, I get 0. The sun, so when I multiply to, I mean, what I'm doing is just this. Sine omega t, sine omega 0 t. This can be written as the, I don't know, is the sum or cosine of the sum or of the difference, okay? So it's the same story again, but in this case, it's just that this delta chi is different from 0 when the molecule is vibrating. So this is, in general, is going to be a linear, the first order is linear combination of the normal coordinates. Remember that the normal coordinates characterize the vibration of the molecule. So this delta J, this delta chi, is going to be a linear combination of the normal coordinates. And then, if this is true, I can do the same trick. I can construct a Raman Hamiltonian, which is going to be roughly E delta P, and this is going to be so this belongs to V squared, and this, since this is a linear combination of vibration of coordinates, this belongs to V. So I have to look for invariance in the product of V squared, symmetry squared, times V. Okay, and that characterizes completely the group theory of vibrational Raman. From the physical viewpoint, at the classical level, I have this amplitude modulation. At the quantum level, what happens is just the following thing. I have my molecule, I have incoming radiation, and then outgoing radiation. With lower energy. Why does it have lower energy? Because this is inelastic scattering. I have some of the modes of the molecule, and I excite these modes from one vibrational level to another vibrational level. Okay, so when this happens, I get the Rayleigh line, omega 0, and I get this one, just because the photon has given part of its energy to a vibrational mode, has excited it. This is called the anti-Stokes, sorry, this is called the Stokes line. And here is the anti-Stokes line, which is just the opposite. In this case, what happens is that one of the vibrational modes loses energy, and that energy is gained by the photon. Okay, anti-Stokes is extremely hard to observe in general, because usually at room temperature, all the vibrational modes of the molecule are in the ground state. Most of them. Why is that? Well, for a very simple reason. The vibrational energies are of the order of 1 eV. Okay. And room temperature, as you know, is 3 Kelvin. The 3 Kelvin is about 1/40 of an eV. Much lower than this. So at room temperature, there are very, very few molecules in excited vibrational state. So anti-Stokes is extremely hard to observe. I mean, this is also not so easy to observe. I mean, stocks, because this thing can be millions of times more intense than this. So, I mean, you need some sophisticated system to do Raman spectroscopy. You have to block completely the center frequency. Okay, so that's the physics. Are there any questions? Okay, so then let's go to the okay, so now I'm going to share. Okay, so now, I mean, I already did the rotational Raman activity. So a molecule is rotational Raman active if its polarizability is anisotropic, because if this is isotropic, it's proportional to the identity, and even when I turn, the identity tensor doesn't change. Now, the polarizability is a symmetric tensor belonging to V square. Now, the polarizability will be anisotropic if the identity representation is contained more than once in V square. And this is only possible if V is reducible. Okay, that's basically what I was saying. I need more than one invariant. If I only have one invariant, that's x squared plus y squared plus z squared, and this is the identity. So this is the criterion. You have rotational Raman activity if the vector representation is reducible. So for methane, it's inactive because this is irreducible, but for deuterated methane, this is active because this thing decomposes. Okay. So now vibrations. As I told you, the vibrations distort the electronic cloud, and now the polarizability it doesn't have all the symmetry of the molecule. It's distorted. There is some distortion. There is some contribution to this. Okay, to the polarizability. Now U belongs to the mechanical representation, so it can be written as before as a linear combination of normal modes, and these are the normal coordinates. So to lowest order, we may assume that this is linear in the coordinates Q. Okay, this is the lowest order. I must tell you that there is also second order Raman spectroscopy when one goes beyond the linear order. And in fact, it's not very hard to, I mean, it's quite simple to obtain the selection rules, but we are not going to do it. Okay, maybe in future problem set, I will give you something to consider quadratic terms in U, okay, or in Q. But to lowest order, these are the dominant terms in scattering. This is just linear in Q, okay? Now, the normal coordinates belong to the vibrational representation. And now I can construct an interaction Hamiltonian that describes the Raman scattering. Remember, the Hamiltonian was the product of the electric field times the dipole moment. The dipole moment is going to be just alpha acting on the electric field. Okay? So alpha ij times aj. And then I have to take the scalar product of this times the electric field. So I reach by a slightly different method the conclusion I already pointed out that this Hamiltonian, the Raman Hamiltonian, lives in V square corresponding to alpha, delta alpha, times V. Now, why is this useful? This is useful because if I consider an energy, something which is a scalar, this thing that I construct, which is linear in the QAs and quadratic in the electric field, has to be an invariant. You see, this is an invariant which is no longer bilinear, it's trilinear invariant. So this is slightly more complicated, but the same thing applies because this thing belongs to V square. So this is in this representation, and it can be decomposed into reducible representation. This thing belongs to V. And if I want to get invariants which are bilinear in products of electric field and Q, or if you want trilinear in electric field and Q, I need to have coincident irreps. Okay. So if I take a vibration mode that belongs to a representation tau, I'll be able to construct an invariant if this tau is also contained in V square. So this is the group theory rule. It's very similar to the infrared activity rule. In infrared activity, a mode was active if the corresponding irrep was in V, because the Hamiltonian was linear in the electric field. Now the Hamiltonian is quadratic in the electric field. So now tau must be contained in V square. So if you know V square, you know immediately which modes are active and which are not. So let's do it. For methane, this is the vibrational representation, which we have already commented on it before. And then the vector representation, you still don't know how to construct this. I'll tell you in next to next lecture. By using projectors or other methods, you can construct symmetry adapted coordinates for more complicated cases like this. Well, this describes quadratic forms in the electric field, and these are the corresponding coordinates. Okay. You don't have to know how to construct this, you will learn, but that's the result. So now I can just construct the Hamiltonian. I'm not going to do it explicitly, I don't know, or do I? No, I don't. But you see that how many invariants can I construct? Well, I can multiply this A1 by this A1. This gives me an invariant, and this tells me that the corresponding frequency is active. This I can multiply by this. So this gives me another invariant, and these two frequencies are also active. And now this I can multiply, this I can multiply, so these two frequencies are also active. And I have a Hamiltonian which depends on 4 independent coefficients. You will do that in an exercise, not construct this. But the important thing is that all 4 frequencies are vibrational Raman active, because all of them are contained in the V square, symmetric V square decomposition representation. So now we understand everything, and we can compute everything in this slide. This, and this. And for the other, it's exactly what you can do it. You will do that at home. But you can obtain the same information for the deuterated method. Okay, so that's the end of today's lecture. Are there any questions? Or...
Okay, if there are no questions, we call it a meeting, and we see each other next week at the same time.